All right, so we wrap up chapter 11 talking about finding areas of regular polygons. So we've talked about quadrilaterals, we've got into circles with circumference and area, and so now we can develop a formula to find the area of additional sided polygons, but only if they're regular. So we have to remember what regular means, right? We have to remember that regular means congruent sides and congruent angles. That's going to help us as we develop the formula here. Okay. Remember first when we were back in chapter 2, circumscribing circles, right? What did it mean to circumscribe a circle? And circumscribe means to draw around, right? So if we're going to circumscribe a circle, that means we're going to draw a circle around something. And the something here is going to be a regular polygon. So if we do that, something like this, if we have a regular hexagon, remember hexagon has 6 sides. If we have a regular hexagon where all the angles, again, remember that all the angles are congruent, right? And then all the sides are congruent. And we circumscribe a circle. Now, what that means is, like I said before, draw around, but specifically draw around so that the circle hits all the vertices of the hexagon. So if we circumscribe a circle, that means all the vertices of this hexagon will be on the circle. Okay? If we do that, then the polygon starts to take on parts of the circle. For example, we know that a circle has a center. Well, since we've circumscribed this circle around the hexagon, that means the hexagon has a center here now. Okay? We know that circles have radii, or you can draw a radius in a circle. Remember, in order to draw a radius in a circle, it has to go from the center to a point on the circle. Now, we can draw a radius in an infinite different ways in a circle, and to an infinite number of points on a circle. So the circle has a radius, and so does a regular polygon, but it's only a radius if that segment goes to the circle that's circumscribed here. And the only way that's going to happen is if you draw that radius to a vertex, because just the vertices of the hexagon are actually on the circle. So while a polygon has a radius now also, you can't draw it in an infinite number of places. You have to draw it to a vertex. So we can draw a radius here, draw a radius here, we can draw a radius here, we can draw a radius here, here, and here. So actually, how many radii can we draw? Just 6. Okay? If this were a regular octagon, then we would be able to draw 8 radii. If it were a regular dodecagon, then we'd be able to draw 12 radii. And so the number of radii we can draw is exactly the same as the number of vertices in that polygon. Okay? Now, let's think a little bit more about this as well. We know that all these sides are congruent in the hexagon, right? All those sides for the hexagon are also chords for this circle, right? If I just worry about drawing this side in, that's a chord for that circle. And we had a theorem back in chapter 10 with our circles, that said if 2 chords were congruent, then the arcs behind them were congruent, right? Here, here. All these arcs are going to be the same. Well, what are all those arc measures? Well, they're all the same. They all have to add to 360, and there's 1, 2, 3, 4, 5, 6 of them. So 360 divided by 6 tells us that all of those arc measures are going to be 60 degrees. Okay? And so we're going to use that idea in just a few minutes as well. All right? All right, some more definitions for you. Okay. Um, the distance from the center to any side of a polygon is called the apothem. New term there for you. So if we were at the center of the polygon and we wanted to know the distance from that center to a side, then we would walk directly at that side, right? And directly at that, I mean at a perpendicular. So the apothem will tell us the distance from the center to the side of that polygon, and that if we were to draw that distance segment in, it would be perpendicular to one of those sides. Okay, now, just like there are 6 radii, I could draw an apothem in 6 different places, and all of those distances would be the same. So it doesn't really matter where the apothem is, as long as it's a segment from the center to the side that's perpendicular. Okay? Now, if we can imagine this circle is still drawn around here, right? Then, like we said before, the sides of this hexagon are also chords for that circle. And we had a theorem in our chapter 10, circle chapter, that said if we drew a segment from the center, it was actually a diameter, but diameter goes through the center. But if we draw a segment from the center and it is perpendicular to a chord, then it also bisects it. So when we draw the apothem in, we know that apothem bisects these sides. So all these pieces are going to be the same. All of this stuff is coming from the idea of drawing a circle around this regular polygon. Okay? And all of these things we're going to need to put together to find the area of a regular polygon. Now, another definition here for you is a central angle. Well, it makes sense that circles have central angles, so then regular polygons are going to have them also. Okay, so again, if we can imagine this circle kind of coming through here, I won't draw the whole circle, then you draw 2 radii and they create a central angle. Here and here are 2 radii for the circle and also 2 radii for the polygon. Now what you know, and this is your central angle, and what we know from circles is that the measure of a central angle is the same as its arc that it's looking at. And we just talked about this, but since this is a hexagon, there are going to be, well, how many central angles? If you draw all the radii in, they're going to be 1, 2, 3, 4, 5, 6. All of these chords that are created on this circle are congruent and therefore 60 degrees. We just talked about that. Then that means all of these angle measures, all of these central angle measures are going to be 60 degrees because central angles and arcs have the same measure. Okay? This is a regular hexagon. It's going to have 6 central angles because I can draw in 6 radii. And therefore, to find the measure of a central angle, it's the same as finding those chords. We would just take 360 divided by 6 and find out that the central angles are 60 degrees. It's something else that we're going to have to do also as we find these areas. Okay? Now, we'll start putting all of this stuff together in just a moment. Quick example here, just so we can pick out center, radius, apothem, and the central angle. Take a look at this diagram and come up with the center for that polygon, the radius for this polygon, the apothem, and then a central angle. Okay, pick those out and then start the video back up and see if you're able to pick them out. Okay, the center of this polygon is at P. A radius would be X, segment XP, or segment PY. If you pick that one out, that's fine too. The apothem is at PQ, and a central angle would be angle XPY. And so just so we can keep reinforcing these ideas, This is a square. It's four-sided. If I wanted to know the measure of this central angle, I would just take 360 divided by 4, because there's going to be 4 of them if you draw in all the radii. And so you get 90. Okay? Okay? All right. Another example here for you to be able to find some angle measures. So in this diagram, ABCDE is a regular pentagon inscribed in circle F. Find each angle measure. So angle AFB. Angle AFB is this central angle. Since it's a pentagon, there are 5 sides. There would be 5 central angles, and since it's regular, they're all going to be the same. So we just divide 360 by 5 and find that AFB is going to be 72 degrees. Okay? AFG, we want to find this angle now. Well, in order to find that angle, we need to understand that if we draw in a radius and the apothem, that basically makes a right triangle. And what we also have to realize is that means all of our right triangle stuff comes back into play here. Pythagorean theorem, sine, cosine, tangent, special right triangles, all that stuff comes back. In this particular situation, it's helpful to realize that since radii are going to be congruent, we've already talked about the apothem bisecting these sides, and the apothem bireflexive is going to be congruent to itself, then by side, 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 these 2 right triangles are going to be congruent, which means that these 2 angles are going to be congruent, which means that the apothem bisects the central angle. So if the central angle is 72 degrees, then angle AFG is going to be half that, or 36. Okay? And then angle GAF is that guy down there. Well, if this angle is 36, then we can just subtract from 90 and get 54. Okay? We need to be able to find those angle measures because, again, we're going to be in right triangles, and sometimes we need angle measures to help us find sides. And the way we do that is using sine, cosine, and tangent. Okay? Now, to the point here in finding areas of a regular polygon. If we want to find the area of this regular polygon, without going into a whole lot of detail, the formula that we're getting ready to talk about that you see here has to do with the fact that if you draw all the radii in, then you create triangles, right? In this hexagon, you make 1, 2, 3, 4, 5, 6 triangles. And so the formula comes from the fact that we're taking these 6 triangles, finding the area of one of them, and multiplying by 6, because they're all going to be the same. All those triangles are going to be the same. So how would you find the area of one of those triangles? Let's say this one. Well, you know the area of a triangle is 1/2 base times height. So 1/2, and then the base is going to be the side length of this regular polygon, and the height is going to be this apothem. So, and then there's going to be 6 of them because there's 6 sides, and so not too surprising, the area formula for a regular polygon turns into 1/2 times the apothem times the side length times the number of sides, 1/2 ASN. Okay? Now, if you take, now since this is a regular polygon, all the sides are the same. So if we added this side plus 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 this side, or the side length times here 6 because it's a hexagon, so the side length times the number of sides, just this right here, then you're basically finding the perimeter. That's why sometimes you see the area formula written like this, where you just need 1/2 times the apothem times the perimeter. Okay? So that's the formula, 1/2 ASN, where S and N come together to create the perimeter. So let's try this. Find the perimeter and the area of this regular polygon. Well, we know the area is 1/2 ASN. Okay? The apothem is 6.5. That's this guy. The side length, we don't know yet. The number of sides, well, this is a pentagon, so 5 sides. How do we go find this side length? Well, with the radius and the apothem, we get a right triangle, so we could do Pythagorean theorem to find this guy, which would be 6.5 squared plus x squared equals 8 squared. So, we do the math here. All right, let's see, 6.5 squared. And then we subtract that from 64. All right, so this is 42.25. Right, so then x squared is going to be equal to 21.75. And we square root both sides, and x ends up being about 4.7. Now, that's just the half of this side. So we've got to double that, so multiply by 2 to find the side length, which is going to be about 9.4. So then the side length is 9.4. We multiply all that together. And you get about 152.75 square units. The perimeter just comes from this, 9.4 times 5. And you get 47. Okay? So I had to use Pythagorean theorem here. Okay? Example number 2 here. This is a nonagon. We want to find the area and the perimeter of a nonagon. So again, area is 1/2 ASN. The apothem, we actually don't know. This 16 is a radius. Remember, the apothem is drawn from the center to a side. So we're going to have to go find the apothem. The side length is 8.48, and since it's a nonagon, it's got 9 sides. So the good news is we can find the perimeter really quickly. Just take 8.48 times 9. Which is 76.32. Now, this apothem, how are we going to find it? Well, if we draw in the apothem, we need to find that. And we know the apothem bisects this side. So if this whole side is 8.48, which it is because it is up here, then this is going to be 4.24. And so we're going to have to do Pythagorean theorem where 16 is the hypotenuse, 4.24 is a leg, and A is a leg. Right? So we take 16 squared and subtract 4.24 squared, and we get 238.02 equals the apothem squared. So now we got to square root both sides and find that the apothem is 15.4. So put 15.4 in here, and then we multiply out. 8.48 times 9 times 0.5, and we get 588.7 square units because it's area. Okay, so still using Pythagorean theorem to find whatever we're missing in this formula. Okay. Example number 3 here. The apothem is what this should say. the apothem and the radius of the regular polygon are drawn below. Find the area. Okay, well, area, 1/2 ASN. The apothem is 2.2. The side length we don't know. And how many sides does it have? 1, 2, 3, 4, 5, 6, 7. So 7. So now go find the side length. Well, we're back to doing Pythagorean theorem again. It's just like we were doing 2 examples ago. Okay? So we're going to set it up so that 2.37 is the hypotenuse, 2.2 is a leg, and we'll do x squared because we know that we're going to have to double this to get the side length. So 2.37 squared minus 2.2 squared gets you 0.7769, which we have to square root. And so x is 0.88. Double that because we need to get the side length. And we get 1.76 in here, and then we're ready to multiply everything out. And we get about 13.6 units squared since it's area. Okay? All right. Now, what happens if you only know one measure? Right? So far we've known 2, either the radius in the apothem or the radius and the side length. Okay? What if we have a regular nonagon that's inscribed in a circle and the radius is 4 units? How do we find the perimeter and the area then? Well, we'd have to find the central angle, and that's not tough. We've talked about this, right? It's a nonagon, so there's going to be 9 central angles. So you divide 360 by 9, and the central angle, this whole central angle, is 40 degrees. Well, remember that means that this smaller angle in here is 20. That means this angle down here is 80. Oh, sorry, not 80, 70. Just subtract from 90. Okay? Well, to do the area, 1/2 ASN, we actually have to have the apothem, which we don't have. It's this guy here. And we have to have the side length, which is this guy here. We don't have that either. So we can use sine, cosine, and tangent to help us find those pieces. Okay? So how? And you see the perimeter and getting to the area here. So we need some more room to do the work. Okay? Well, this triangle is just this one pulled out. So let's work off of it. Okay? This angle is 20. We just talked about how. This one's 70. Again, we just talked about how. Well, I need to find the apothem, and we need to find half the side length. Well, from this angle in this right triangle, then we are looking for the opposite side, and we know the hypotenuse, and that's sine. Sine does that. So we can write the equation, sine of 20 degrees equals opposite over hypotenuse, and be able to find half that side length. Now, since x is up high, we're going to multiply. Okay, and so half that side length is going to be 1.37, which we're going to double. So the side length ends up being 2.74. Now that we know the side length, we can actually find the perimeter, right? Because again, it's the side length times the number of sides. It's n and s. And so n is 9, s is 2.74. We find the perimeter that way. I want to, so multiply this by 9. And the perimeter is 24.6. Now, we also need the apothem in order to get the area. So we go back to our right triangle from this angle here, which is 20 degrees. We know the hypotenuse, and we need to find the adjacent. And so that's cosine. So cosine of 20 is equal to the adjacent over the hypotenuse. Since A is up high, we're going to multiply 4 times cosine 20. And we get 3.76 as the apothem. So, find the area. We take 1/2 times 3.76 times 24.6 as the parameter. Okay? And the area turns into 46.23 units squared. Okay? So sometimes you're going to have to use sine, cosine, and tangent. All right. One more example here. And I'm going to be honest with you, I don't have these lengths. So they're in your notes. So let's just talk generically about it, and you can use the numbers in your notes. We need to find the area of the shaded region. The shaded region is in your notes, is the blue region here. Well, easy enough, right? We just need to find the area of the circle, which is pi r squared, right? And this is r, that's your radius. When we find that, then we're just going to subtract out the area of this regular polygon, 1/2 ASN. So the apothem, I believe, has been given to you, and I can't remember if the radius was or not. But anyway, the numbers that you're looking at in your example, you should be able to. You're going to have to do Pythagorean theorem to find one of the missing side there and be able to go through this. But you're going to have to take the total area, the shaded region, is just going to be this area of the circle minus the area of this regular polygon. So using what we've talked about before, you should be able to take care of that. Okay? And so that's it. Hopefully that gets you through. Try the homework. I know this is kind of crazy stuff. We'll take care of any questions that you have in class next time. Okay?